Space is the final frontier, a place of wonder, mystery, and exploration. But it is also a place of unimaginable danger. Every mission into space involves risks, and the cold, unforgiving environment of the cosmos presents some of the most terrifying ways to meet one's end. The vacuum of space is not just empty, it is hostile to human life in ways that most people cannot even imagine. When we look up at the night sky, we see beauty and wonder. We see distant stars twinkling like diamonds against the velvet darkness. We see the moon casting its gentle glow across the landscape. We see the vast expanse of the universe stretching out before us, inviting us to explore and discover. But what we do not see are the countless dangers that lurk in that seemingly peaceful void. The human body was designed for life on Earth. We need air to breathe, water to drink, and a stable temperature to survive. We need protection from radiation, and we need gravity to keep our bones strong and our muscles working properly. Space provides none of these things. Instead, it offers a harsh environment where the slightest mistake can lead to death within seconds. Astronauts who venture into space are some of the bravest individuals on Earth. They know the risks, they understand the dangers, and yet they still choose to leave the safety of our planet behind. They do this in the name of science, exploration, and the betterment of humanity. But every time they step into a spacecraft, they are entering a realm where death is always just one malfunction away. The dangers of space are not just theoretical. Throughout the history of space exploration, we have lost brave men and women to the hostile environment of the cosmos. Some died in explosions during launch, others suffocated when their life support systems failed, and still others were killed by the extreme conditions they encountered in the void. Each of these tragedies serves as a reminder of just how dangerous space travel really is. In the pages that follow, we will explore the various ways that space can kill. We will examine the science behind these dangers, and we will look at real-world examples of what happens when things go wrong. We will discuss the vacuum of space, the extreme temperatures, the deadly radiation, and the countless other hazards that await those who dare to venture beyond our atmosphere. This is not a story of fear, but rather a story of respect. Respect for the dangers of space, respect for the courage of those who explore it, and respect for the incredible engineering and planning that goes into every mission. By understanding these dangers, we can better appreciate the incredible achievements of space exploration and the remarkable bravery of those who make it possible. Join us as we explore the most horrific ways to die in space, understanding the real dangers that await those brave enough to venture into the unknown. We will journey through the cold vacuum of space, witness the effects of extreme temperatures, and examine the silent killer that is cosmic radiation. We will see how spacecraft malfunctions can turn life-saving vessels into death traps, and how the psychological pressures of space travel can push even the most trained astronauts to their breaking point. The universe is vast and beautiful, but it is also deadly. For those who choose to explore it, the risks are real and the consequences are final. Yet despite these dangers, humans continue to push the boundaries of exploration, driven by an insatiable curiosity about what lies beyond our world. This is the story of those who risk everything to expand the frontiers of human knowledge, and the ultimate price that some of them pay for their courage. The vacuum of space is perhaps the most immediate and terrifying threat facing any human who ventures beyond Earth's protective atmosphere. Unlike the air we breathe on Earth, space contains virtually nothing at all. No oxygen, no nitrogen, no water vapor, just an endless void that stretches between the stars. This emptiness is not just an inconvenience, it is a death sentence for any unprotected human being. When we think about the vacuum of space, we often imagine it as simply a place without air. But the reality is far more complex and frightening. The vacuum of space is a complete absence of matter, creating conditions that the human body simply cannot survive. The pressure difference between the inside of a human body and the vacuum of space is so extreme that it creates a cascade of deadly effects that can kill within minutes. On Earth, we live under the constant pressure of our atmosphere. This pressure, measured at about 14 7/10 pounds per square inch at sea level, is what keeps our bodies functioning normally. Our blood, our organs, and even the water in our cells all exist in equilibrium with this atmospheric pressure. Remove that pressure suddenly, and the human body begins to tear itself apart from the inside out. The first thing that happens when a human is exposed to the vacuum of space is rapid decompression. The air in the lungs immediately begins to expand, and if the person tries to hold their breath, their lungs will rupture like overinflated balloons. The smart thing to do, if you ever find yourself in this situation, is to exhale immediately and continuously. This prevents the lungs from bursting, but it also means that all the oxygen in your body is quickly expelled into space. Without oxygen, the human brain can only function for about 10 to 15 seconds before consciousness is lost. This is actually a mercy, because what happens next is even more horrifying. As the pressure drops, the saliva on your tongue begins to boil, the water in your blood starts to vaporize, creating bubbles that block circulation. This condition, known as ebulism, causes the body to swell to nearly twice its normal size as fluids throughout the body begin to boil and expand. The swelling is not just uncomfortable, it is agonizing. The skin stretches to its limits, and while it is strong enough to prevent the body from actually exploding, the pain would be unbearable if the person were still conscious. The eyes begin to bulge from their sockets as the fluid inside them vaporizes. The tongue swells to enormous proportions, and the entire body becomes a grotesque parody of its former self. But the vacuum of space is not finished with its victim yet. The temperature in space varies dramatically depending on whether you are in sunlight or shadow. In direct sunlight, temperatures can reach over 250 degrees Fahrenheit. In the shadow of a planet or spacecraft, temperatures can drop to nearly -400 degrees Fahrenheit. These extreme temperatures begin to affect the body immediately. If you are in direct sunlight, the side of your body facing the sun will begin to burn and blister within minutes. The skin will turn red, then black, as the cells are destroyed by the intense heat. At the same time, the side of your body facing away from the sun will begin to freeze. The water in your cells will turn to ice, causing the cells to rupture and die. You become a living example of the extreme temperature differences that exist in space. The lack of atmospheric pressure also affects the body in other ways. Without the pressure of the atmosphere to hold everything in place, the body begins to lose its shape. The internal organs shift and move in ways they were never meant to. The heart struggles to pump blood that is now full of vapor bubbles. The kidneys cannot filter blood that is boiling. The liver cannot process toxins that are expanding and contracting with each bubble of vaporized fluid. Even if by some miracle the person could be rescued and brought back to a pressurized environment, the damage would already be done. The lack of oxygen would have caused irreversible brain damage within minutes. The effects of ebulism would have damaged blood vessels throughout the body. The extreme temperatures would have caused severe burns and frostbite. The victim would likely never recover, and death would be inevitable. This is why spacesuits are so incredibly important. They are not just clothing, they are life support systems that maintain the pressure and temperature that the human body needs to survive. Every seal, every valve, every connection is a matter of life and death. A single tear in a spacesuit, a single malfunctioning valve, can mean the difference between a successful mission and a horrible death in the void. The vacuum of space is patient and relentless. It does not care about human ambition or courage. It does not care about the importance of the mission or the lives that depend on it. It simply waits, ready to claim any human who dares to venture into its domain without proper protection. In the cold, empty void between the stars, the vacuum of space remains the ultimate silent killer, always ready to remind us of our own fragility in the face of the infinite cosmos. The history of space exploration is filled with reminders of just how dangerous the vacuum can be. During the early days of the Soviet space program, there were numerous incidents where cosmonauts came dangerously close to experiencing the full horror of vacuum exposure. Test pilots who flew experimental aircraft to the edge of space reported feeling their saliva begin to bubble on their tongues when their pressure suits malfunctioned at extreme altitudes. One of the most terrifying aspects of vacuum exposure is how quickly it can happen. A spacecraft traveling at thousands of miles per hour can be punctured by a piece of debris no larger than a marble. The resulting hole, even if it is only a few inches across, can cause catastrophic decompression in a matter of seconds. The air rushes out with such force that it can actually push objects and people toward the breach, making it nearly impossible to seal the hole before it is too late. The psychological impact of vacuum exposure cannot be understated. Astronauts who have experienced minor decompression events describe a feeling of absolute terror as they realize what is happening. The body begins to react instinctively, trying to hold onto the air that is rapidly escaping. The mind races through emergency procedures, while simultaneously being overwhelmed by the knowledge that death is only moments away. Training for vacuum exposure is one of the most challenging aspects of astronaut preparation. Candidates must learn to overcome their natural instincts and follow specific procedures, even when their bodies are screaming at them to panic. They practice emergency decompression scenarios over and over again, learning to exhale continuously, activate emergency oxygen supplies, and seal breaches in their suits or spacecraft. The equipment designed to protect astronauts from vacuum exposure is incredibly sophisticated, but it is also incredibly fragile. A spacesuit is essentially a miniature spacecraft, complete with life support systems, pressure regulation, and temperature control. Every component must work perfectly, because even the smallest failure can be fatal. The suits are tested extensively on Earth, but the true test comes only when they are used in the actual vacuum of space. Even with all the safety measures and backup systems, the vacuum of space remains an ever-present threat. Every spacewalk, every mission outside the protective hull of a spacecraft is a calculated risk. The astronauts who undertake these missions are fully aware of the dangers, yet they continue to push the boundaries of human exploration. They do so knowing that one day, the vacuum of space may claim another victim. The engineering challenges of protecting humans from vacuum exposure continue to evolve as we plan missions to more distant destinations. A journey to Mars would expose astronauts to the vacuum of space for months at a time, increasing the likelihood of equipment failure or catastrophic decompression. The spacesuits and spacecraft of the future will need to be even more reliable and robust than those we use today. Despite all the technological advances and safety improvements, there is one inescapable truth about space exploration. The vacuum of space will always be there, waiting patiently for any human who dares to venture beyond the protective embrace of Earth's atmosphere. It is a reminder that space is not meant for human life, and that every mission into the void is an act of defiance against the natural order of the universe. In the end, the vacuum of space represents the ultimate test of human ingenuity and courage. It is a challenge that we must meet with the best technology, the most rigorous training, and the deepest respect for the dangers that await us in the cosmos. For those who choose to explore the final frontier, the vacuum of space will always be their most formidable and unforgiving opponent. The temperature extremes of space are beyond anything that exists naturally on Earth. While we complain about a hot summer day or a cold winter night, these earthly temperature variations are nothing compared to what awaits in the void between worlds. Space, is a realm of impossible contrasts, where the difference between sunlight and shadow can mean the difference between burning alive and freezing to death. In the direct rays of the sun, with no atmosphere to filter or diffuse the radiation, temperatures can soar to over 250 degrees Fahrenheit. This is hot enough to boil water, hot enough to melt lead, and certainly hot enough to kill a human being in a matter of minutes. The sun's energy, unfiltered by any protective atmosphere, strikes with the full force of a star that burns at millions of degrees at its core. But step into shadow, and the temperature plummets to nearly minus 400 degrees Fahrenheit. This is colder than anything found naturally on Earth. Colder than the coldest winter night in Antarctica. Colder than liquid nitrogen. At these temperatures, the human body would freeze solid in minutes, every cell turning to ice, every organ becoming as brittle as glass. The human body is designed to operate within a very narrow temperature range. Our normal body temperature is 98.6 degrees Fahrenheit, and even small variations from this norm can cause serious problems. A fever of just a few degrees can make us feel sick and weak. A drop in body temperature of just 10 degrees can cause hypothermia and death. Now imagine being exposed to temperatures that vary by more than 600 degrees, depending on whether you are in sunlight or shadow. When exposed to the extreme heat of direct sunlight in space, the human body begins to cook from the outside in. The skin, which is our first line of defense against temperature extremes, quickly becomes overwhelmed. Within minutes, the exposed skin begins to turn red, then blister, then blacken as the cells are literally cooked by the intense heat. The pain would be excruciating, like being pressed against a red-hot stove, but covering the entire body. The heat penetrates deeper with each passing moment. The subcutaneous fat beneath the skin begins to melt and bubble. The muscle tissue starts to denature, breaking down at the molecular level, like meat in an oven. The blood vessels dilate in a desperate attempt to cool the body, but there is no cool air to provide relief, only the relentless heat of an unfiltered star. As the internal temperature rises, the body's cooling mechanisms begin to fail. Sweating becomes useless because the sweat evaporates instantly in the vacuum of space. The heart races as it tries to pump blood to cool the overheating organs, but the blood itself is becoming heated to dangerous levels. The brain, which is particularly sensitive to temperature changes, begins to malfunction as proteins denature and neurons die. But the horror of extreme heat is matched by the terror of extreme cold. When an astronaut moves from sunlight into shadow, the temperature drops so rapidly that the body cannot adapt. The extremities, fingers and toes, are the first to freeze. The blood vessels constrict in an attempt to preserve core body temperature, but this only accelerates the freezing process in the hands and feet. As the cold penetrates deeper, the skin becomes hard and brittle. Ice crystals form in the cells, puncturing cell walls and causing massive tissue damage. The muscles become stiff and unresponsive, making it impossible to move or manipulate equipment. The joints freeze in place, turning the body into a rigid, ice-covered statue. The cold affects the internal organs as well. The heart struggles to pump blood that is becoming increasingly thick and sluggish as it cools. The lungs find it difficult to process the frigid air, and breathing becomes painful and labored. The kidneys begin to shut down as the cold blood flowing through them drops below the temperature needed for proper function. Perhaps most terrifying of all is the effect on the brain. As the temperature drops, mental function begins to deteriorate. Thoughts become confused and disorganized. Memory fails. The ability to make rational decisions disappears. The victim may not even realize what is happening as hypothermia takes hold and consciousness fades away. The challenge of surviving these temperature extremes is compounded by the fact that they can change rapidly. An astronaut performing a spacewalk might move from the blazing heat of direct sunlight to the frigid cold of shadow in a matter of seconds. The body simply cannot adapt to such rapid changes, and the thermal shock alone can be fatal. Spacesuits are designed to protect astronauts from these extreme temperatures, but they are not perfect. The suits contain layers of insulation and reflective materials to regulate temperature, but they are complex systems that can fail. A malfunction in the suit's cooling system while in direct sunlight could result in death from overheating within minutes. A failure in the heating system while in shadow could result in death from hypothermia just as quickly. The Apollo missions to the Moon provided real-world examples of these temperature extremes. The lunar surface, with no atmosphere to moderate temperatures, experiences swings from over 200 degrees Fahrenheit in sunlight to minus 250 degrees Fahrenheit in shadow. The astronauts who walked on the Moon were completely dependent on their spacesuits to keep them alive in this hostile environment. During the Apollo missions, there were several close calls related to temperature extremes. Astronauts reported feeling uncomfortably hot when working in direct sunlight, even with their suits' cooling systems running at full capacity. Others experienced cold spots where the suit's heating system was not functioning properly, leading to numbness and reduced dexterity in their extremities. The psychological impact of experiencing these temperature extremes cannot be underestimated. Astronauts describe the sensation of moving from sunlight to shadow as profoundly unsettling. The immediate change from blazing heat to bitter cold serves as a constant reminder of just how hostile the space environment really is. It is a reminder that they are completely dependent on their technology for survival, and that any failure could mean death. Future missions to Mars and beyond will face even greater temperature challenges. The journey to Mars takes months, during which astronauts will be exposed to the temperature extremes of deep space for extended periods. The spacecraft will need to be designed to handle these conditions, and the life support systems will need to be incredibly reliable. The extreme temperatures of space serve as a constant reminder that the universe is not designed for human life. We are creatures of a temperate planet, adapted to live within a narrow range of conditions. When we venture into space, we are entering a realm where the very environment itself is trying to kill us. The heat that can cook us alive and the cold that can freeze us solid are always there, waiting for any failure in our protective systems. In space, temperature is not just a matter of comfort, it is a matter of life and death. The extreme heat and cold that exist in the void between worlds represent some of the most immediate and terrifying dangers that astronauts face. These temperature extremes push the human body beyond its limits, creating conditions that can kill within minutes. For those who choose to explore the cosmos, the battle against these temperature extremes is a fight for survival that never ends. The engineering challenges of protecting humans from these temperature extremes are staggering. Spacesuits must function as miniature climate control systems, maintaining a stable internal temperature despite being exposed to conditions that would destroy most materials. The outer layers of a spacesuit are designed to reflect heat and radiation, while inner layers provide insulation against the cold. Between these layers, cooling tubes circulate chilled water to remove excess heat, while heating elements warm critical areas when needed. But even the most sophisticated spacesuit has its limits. During the Gemini program, astronaut Edward White experienced severe overheating during America's first spacewalk. His suit's cooling system was overwhelmed by the combination of physical exertion and direct sunlight, causing his heart rate to soar and his visor to fog with perspiration. He was forced to cut short his historic spacewalk to prevent potentially fatal overheating. The International Space Station provides a perfect example of how temperature extremes affect spacecraft design. The station orbits Earth every 90 minutes, meaning it experiences 16 sunrises and sunsets each day. During each orbit, the station is exposed to the full heat of the sun for about 45 minutes, followed by 45 minutes of frigid darkness. This constant cycling between extreme temperatures puts enormous stress on the station's structure and systems. The station's solar panels, which provide power for the entire facility, must be designed to withstand these temperature swings without warping or cracking. The main body of the station is covered with thermal blankets and radiators to manage heat, while internal heaters keep critical systems warm during the cold periods. Despite these precautions, astronauts aboard the station report feeling the effects of these temperature cycles, with some areas of the station becoming uncomfortably warm, while others remain persistently cold. The psychological effects of these temperature extremes extend beyond mere physical discomfort. Astronauts describe feeling profoundly isolated when they realize that the familiar sensations of earthly weather, warm breezes, cool rain, seasonal changes, simply do not exist in space. The harsh binary of blazing heat and freezing cold serves as a constant reminder that they are in an alien environment where the basic conditions necessary for life must be artificially maintained. During long-duration missions, the mental strain of constantly monitoring temperature systems and worrying about potential failures can be overwhelming. Astronauts must remain vigilant for signs of overheating or overcooling, knowing that either condition could quickly become fatal. The knowledge that they are always just one system failure away from experiencing these deadly extremes creates a level of stress that is difficult to imagine. The effects of temperature extremes on the human body are not always immediately fatal, but they can cause lasting damage that may not become apparent until years later. Repeated exposure to thermal stress can damage the cardiovascular system, making the heart work harder to regulate body temperature. The skin, constantly stressed by temperature variations, may develop chronic conditions or become more susceptible to injury. Prolonged exposure to cold, even within the protected environment of a spacecraft, can cause subtle changes in bone density and muscle mass. The body's attempts to conserve heat can redirect blood flow away from the extremities, leading to chronic circulation problems. Some astronauts report persistent cold sensitivity in their hands and feet long after returning to Earth, a possible result of repeated thermal stress during their missions. The development of new technologies to protect astronauts from temperature extremes is an ongoing challenge. Researchers are working on advanced materials that can provide better insulation while remaining lightweight and flexible. New cooling systems are being developed that can more efficiently remove heat from the body while using less power and water. Heating elements are being redesigned to provide more uniform warmth while reducing the risk of hotspots that could cause burns. One of the most promising developments is the creation of phase change materials that can absorb and release heat as they change from solid to liquid and back again. These materials can help smooth out temperature fluctuations, providing a buffer against rapid temperature changes. They are being incorporated into the next generation of spacesuits and spacecraft thermal management systems. The challenges become even greater when considering future missions to the outer planets. A journey to Jupiter would expose astronauts to the extreme cold of the outer solar system, where sunlight is 27 times weaker than it is near Earth. The spacecraft would need to carry its own heat source, likely a nuclear reactor, to maintain livable temperatures during the multi-year journey. The psychological impact of traveling through such cold, dark regions of space would be immense. Mars presents its own unique temperature challenges. The planet's thin atmosphere provides little protection from temperature extremes, and the surface temperature can vary from a relatively warm 70 degrees Fahrenheit near the equator during summer to minus 195 degrees Fahrenheit at the poles during winter. Astronauts living on Mars would need to deal with these temperature variations, while also contending with massive dust storms that can block sunlight and affect heating systems. The history of space exploration is filled with examples of how temperature extremes have threatened human life. During the Apollo 13 crisis, the crew faced the very real possibility of freezing to death as they powered down their spacecraft to conserve energy. the temperature inside the lunar module dropped to just above freezing, and the astronauts had to huddle together for warmth while wearing multiple layers of clothing. They described the experience as being trapped in a refrigerator, with condensation forming on every surface and their breath visible in the frigid air. The Soviet space program also experienced temperature-related emergencies. During the Soyuz 11 mission, the crew faced overheating problems when their spacecraft's cooling system malfunctioned. The temperature inside the capsule rose to dangerous levels, and the cosmonauts had to remove their spacesuits to avoid heat stroke. Tragically, this decision would later contribute to their deaths when the cabin depressurized during re-entry. These incidents highlight the critical importance of thermal management systems in space exploration. Every spacecraft, every spacesuit, every piece of equipment must be designed to function in the extreme temperature environment of space. The margin for error is essentially zero, because the consequences of failure are almost always fatal. The temperatures of space are not just extremes of hot and cold. They are the difference between life and death, pushing the human body beyond its limits and challenging our technology to its breaking point. For those who choose to venture into the cosmos, the battle against these temperature extremes is a constant struggle, one that requires the best of human engineering and the courage to face an environment that is fundamentally hostile to life itself. Radiation is perhaps the most insidious and terrifying threat that astronauts face in space. Unlike the vacuum or extreme temperatures, which kill quickly and obviously, radiation works slowly and silently, damaging the body at the cellular level in ways that may not become apparent for months or even years. It is a killer that strikes without warning, leaving no immediate trace of its deadly work until it is far too late to do anything about it. On Earth, we are protected from the worst effects of cosmic radiation by our planet's magnetic field and thick atmosphere. These natural shields deflect or absorb most of the high-energy particles that constantly bombard our solar system from deep space. But venture beyond this protective cocoon, and you enter a realm where radiation levels are hundreds or even thousands of times higher than anything experienced on Earth. Cosmic radiation comes from many sources throughout the universe. Some of it originates from our own sun, which constantly emits a stream of charged particles known as the solar wind. Other radiation comes from distant stars that have exploded in spectacular supernovas, sending high-energy particles racing across the galaxy at nearly the speed of light. Still more radiation comes from the mysterious depths of space itself, from sources so distant and powerful that we can barely comprehend their origins. The human body simply was not designed to withstand this constant bombardment of high-energy particles. Each particle that strikes a cell has the potential to damage or destroy the DNA within that cell. Most of the time, the body's natural repair mechanisms can fix this damage or cause the damaged cell to die before it can cause problems. But when the radiation exposure is intense enough or goes on long enough, the body's defenses are overwhelmed. The first sign of serious radiation exposure is often radiation sickness, a condition that can begin within hours of exposure to high levels of radiation. The symptoms start subtly, with nausea, vomiting, and fatigue that might be mistaken for space sickness or stress. But as the condition progresses, the symptoms become more severe and unmistakable. The victim experiences severe diarrhea, high fever, and extreme weakness as their immune system begins to shut down. As radiation sickness progresses, the body's ability to produce new blood cells is destroyed. The bone marrow, which is responsible for creating red blood cells, white blood cells, and platelets, begins to fail. Without enough red blood cells, the victim becomes anemic and weak. Without enough white blood cells, they become vulnerable to infections that their body cannot fight off. Without enough platelets, they begin to bleed internally as their blood loses the ability to clot. In the final stages of acute radiation sickness, the victim experiences what medical professionals grimly refer to as the walking ghost phase. During this period, which can last for days or weeks, the person may feel relatively normal and even be able to function normally. But inside their body, massive cellular damage is occurring. Their immune system is completely destroyed, their digestive system is breaking down, and their organs are beginning to fail one by one. Death from acute radiation sickness is neither quick nor painless. The victim typically dies from multiple organ failure, severe infection, or massive internal bleeding. Throughout this process, they remain conscious and aware of what is happening to them, making it one of the most psychologically traumatic ways to die. The knowledge that the damage has already been done and that death is inevitable adds a layer of psychological horror to the physical suffering. But acute radiation sickness is not the only danger posed by cosmic radiation. Even lower levels of exposure, the kind that astronauts might experience during a long mission to Mars, can cause serious long-term health problems. The most well-known of these is cancer, which can develop years or decades after the initial radiation exposure. Cancer occurs when radiation damage to DNA causes cells to grow and divide uncontrollably. The more radiation exposure a person receives, the higher their risk of developing cancer later in life. For astronauts on long-duration missions, this increased cancer risk is a very real concern. Studies of atomic bomb survivors and nuclear workers have shown that even relatively low levels of radiation exposure can significantly increase the risk of leukemia, lung cancer, breast cancer, and many other types of cancer. The risk is not just to the astronauts themselves, but potentially to their future children as well. Radiation can damage the reproductive cells, causing genetic mutations that can be passed on to the next generation. These mutations can cause birth defects, developmental disabilities, or increased susceptibility to various diseases. The thought that a mission to explore space could harm not just the astronauts, but their descendants as well, adds another layer of moral complexity to space exploration. The Sun, our life-giving star, can also become a deadly source of radiation. Solar flares and coronal mass ejections can send massive bursts of high-energy particles racing toward Earth at millions of miles per hour. When these solar storms strike, they can deliver radiation doses that are immediately lethal to any unprotected human in space. During a major solar storm, radiation levels in space can increase by a factor of 1,000 or more within minutes. An astronaut caught outside a spacecraft during such an event would receive a lethal dose of radiation in less than an hour. Even inside a spacecraft, the radiation levels can become dangerously high, potentially causing radiation sickness or increasing the long-term risk of cancer. The unpredictable nature of solar storms makes them particularly frightening. While scientists can monitor the Sun for signs of increased activity, they cannot predict exactly when a major solar storm will occur or how intense it will be. This means that astronauts must always be prepared for the possibility of a radiation emergency, and spacecraft must be designed with adequate shielding to protect the crew during these events. The Van Allen radiation belts, which surround Earth like invisible donuts, present another radiation hazard for space travelers. These belts contain high concentrations of charged particles trapped by Earth's magnetic field. While they help protect us from cosmic radiation by deflecting many particles away from Earth, they also create regions of intense radiation that spacecraft must pass through when traveling to and from Earth orbit. The Apollo astronauts had to pass through the Van Allen belts on their way to the Moon, exposing them to significant radiation doses during their brief transit. Future missions to Mars or other destinations will require astronauts to spend much longer periods in these radiation-rich regions of space, potentially receiving dangerous levels of exposure before they even begin their main mission. The challenge of protecting astronauts from radiation is one of the most difficult problems facing space exploration. Unlike temperature or pressure, which can be controlled with relatively straightforward engineering solutions, radiation is much harder to shield against. The high-energy particles that make up cosmic radiation can penetrate most materials, including the aluminum hulls of spacecraft. Traditional radiation shielding, like the lead aprons used in medical X-ray procedures, is far too heavy to be practical for spacecraft. Engineers have experimented with various materials and designs, including water-filled walls, plastic polymers, and magnetic fields, but each solution has its own drawbacks. Water is heavy and can freeze in the cold of space. Plastics can become brittle when exposed to radiation. Magnetic fields require enormous amounts of power to generate. Some of the most promising research involves using the spacecraft's own supplies as radiation shielding. Water, food, and other consumables can be arranged around the crew compartment to provide some protection from radiation. This approach has the advantage of using materials that are already needed for the mission, but it provides only limited protection and becomes less effective as supplies are consumed. The psychological impact of radiation exposure cannot be ignored. Unlike other space hazards, which are immediate and obvious, radiation damage occurs silently and invisibly. Astronauts must live with the knowledge that every moment they spend in space, their bodies are being bombarded with particles that could be slowly killing them. This creates a unique form of psychological stress that can affect decision-making and mental health during long missions. The uncertainty surrounding radiation effects makes this psychological burden even heavier. While scientists have a general understanding of how radiation affects the human body, there is still much that is unknown about the long-term effects of the type of radiation exposure that astronauts experience. This uncertainty means that astronauts cannot know for certain what health problems they might face in the future as a result of their missions. Future missions to Mars and beyond will expose astronauts to radiation levels that are far higher than anything experienced by previous space travelers. The journey to Mars takes months, during which astronauts will be exposed to the full intensity of cosmic radiation, with no protection from Earth's magnetic field or atmosphere. Once on Mars, they will continue to be exposed to high levels of radiation due to the planet's thin atmosphere and weak magnetic field. The cumulative radiation dose from a mission to Mars could be equivalent to receiving hundreds of chest X-rays or being exposed to the radiation from a nuclear accident. This level of exposure significantly increases the risk of cancer and other radiation-related health problems. Some scientists estimate that the radiation exposure from a Mars mission could increase an astronaut's lifetime cancer risk by as much as 5%. The ethical implications of sending astronauts on missions with such high radiation exposure are profound. Space agencies must weigh the scientific benefits of exploration against the health risks to the astronauts. They must also consider whether it is acceptable to ask people to accept such risks, even if they volunteer to do so with full knowledge of the dangers. Research into radiation protection continues, with scientists exploring everything from pharmaceutical interventions that could help the body repair radiation damage to advanced materials that could provide better shielding while remaining lightweight. Some researchers are even investigating the possibility of using genetic engineering to make humans more resistant to radiation, though such approaches raise their own ethical questions. The development of more sophisticated radiation detection and monitoring systems is also crucial. Astronauts need real-time information about radiation levels so they can take appropriate protective measures when necessary. This might involve retreating to a more heavily shielded area of the spacecraft during a solar storm, or altering mission plans to avoid periods of high radiation exposure. Despite all these challenges, the exploration of space continues, driven by humanity's insatiable curiosity about the universe beyond our planet. But radiation remains one of the most serious obstacles to long-term space exploration. A silent killer that could claim the lives of those brave enough to venture into the depths of space. In the vast expanse of the cosmos, radiation serves as a constant reminder that space is not meant for human life, and that every journey beyond Earth's protective embrace is a gamble with forces that we are only beginning to understand. The invisible threat of radiation may be silent, but its effects are all too real. For those who choose to explore the final frontier, the battle against this unseen enemy will be one of the greatest challenges they face, a fight for survival that begins the moment they leave Earth's protective embrace and continues until they return safely home. Of all the ways to die in space, suffocation is perhaps the most intimately terrifying because it mirrors our most basic fear of being unable to breathe. Every human being has experienced that moment of panic when they hold their breath too long or when something briefly blocks their airway. In space, that panic becomes a deadly reality where the simple act of breathing, something we do automatically thousands of times each day, becomes a matter of life and death. Oxygen is the most immediate necessity for human survival. While a person can survive for days without water and weeks without food, the brain begins to suffer irreversible damage after just 4 to 6 minutes without oxygen. In the hostile environment of space, where there is no breathable atmosphere and where life support systems can fail without warning, the threat of suffocation is constant and immediate. The human respiratory system evolved to function in Earth's atmosphere, which contains approximately 21% oxygen, 78% nitrogen, and small amounts of other gases, all at a pressure of about 14 7/10 pounds per square inch. This precise combination allows our lungs to efficiently extract oxygen from the air and deliver it to our bloodstream, where it is carried to every cell in our body. In space, there is no air at all. The vacuum contains no oxygen, no nitrogen, nothing that the human respiratory system can use. An astronaut who removes their helmet in space or whose suit is punctured will find themselves in an environment where breathing is not just difficult, it is impossible. The lack of air pressure means that even if oxygen were somehow available, the lungs could not function properly to extract it. The process of suffocation in space begins almost immediately upon exposure to vacuum. As we discussed earlier, the smart response to sudden decompression is to exhale immediately and continuously. This prevents the lungs from rupturing due to the expanding air inside them. But it also means that all the oxygen in the lungs is quickly expelled into space, leaving nothing for the body to use. Once the lungs are empty, the body begins to consume the oxygen that remains in the bloodstream. The heart continues to pump this oxygen-rich blood to the brain and other vital organs, but without any way to replenish the oxygen supply, this reserve is quickly depleted. Within 10 to 15 seconds, the oxygen levels in the brain drop low enough to cause unconsciousness. This rapid loss of consciousness is actually merciful, because what happens next would be unbearable to experience while awake. As the oxygen levels continue to drop, the brain begins to shut down non-essential functions in a desperate attempt to preserve the most critical areas. Memory formation stops, so the victim cannot form new memories of their ordeal. Motor control is lost, so they cannot move or struggle. Eventually, even the basic functions that keep the heart beating and the lungs trying to breathe begin to fail. The body does not give up easily. Even without conscious control, the respiratory system continues to attempt to breathe. The diaphragm contracts and relaxes in increasingly desperate attempts to draw air into the lungs. But in the vacuum of space, these efforts are futile. There is simply nothing to breathe. The chest rises and falls in a grotesque parody of normal breathing, but no life-giving oxygen enters the body. As the minutes pass, the lack of oxygen begins to cause irreversible damage throughout the body. The brain, which consumes about 20% of the body's oxygen supply under normal conditions, is particularly vulnerable. Brain cells begin to die within minutes of being deprived of oxygen. starting with the most complex functions like consciousness and memory, and progressing to the basic functions that control breathing and heart rate. The heart, meanwhile, continues to beat for several minutes after breathing stops, but its rhythm becomes increasingly erratic as the cardiac muscle is deprived of oxygen. The heart may race as it tries to circulate what little oxygenated blood remains, or it may slow dramatically as the cardiac cells begin to fail. Eventually, the heart stops beating altogether and clinical death occurs. But suffocation in space is not always the result of sudden decompression. More commonly, it results from failures in the complex life support systems that maintain breathable air inside spacecraft and spacesuits. These systems must not only provide oxygen, but also remove carbon dioxide, control humidity, and maintain proper air pressure. A failure in any of these systems can quickly create a life-threatening situation. Spacecraft life support systems are marvels of engineering, designed to create and maintain a small bubble of Earth-like atmosphere in the hostile environment of space. They must continuously generate or recycle oxygen, scrub carbon dioxide from the air, and monitor air quality to ensure that the atmosphere remains safe to breathe. These systems are typically redundant, with multiple backup systems to prevent catastrophic failure, but they are also complex and can malfunction in ways that are not immediately obvious. One of the most insidious forms of suffocation occurs when the oxygen levels gradually decline due to a slow leak or system malfunction. Unlike sudden decompression, which causes immediate symptoms, a gradual loss of oxygen can go unnoticed until it is too late. The human body is surprisingly poor at detecting low oxygen levels, especially when the decline is gradual. The symptoms of oxygen deprivation, known medically as hypoxia, begin subtly. The victim may feel slightly lightheaded or experience a mild headache. They might become slightly confused or have difficulty concentrating. These symptoms are easily dismissed as fatigue or stress, especially in the high-pressure environment of a space mission, where astronauts are expected to perform complex tasks under difficult conditions. As the oxygen levels continue to drop, the symptoms become more pronounced, but they may still be mistaken for other problems. The victim may become euphoric or giddy, a condition known as hypoxic euphoria. They may feel overconfident or make poor decisions without realizing that their judgment is impaired. This false sense of well-being can be deadly, as it prevents the victim from recognizing the danger they are in and taking appropriate action. By the time the symptoms become severe enough to be recognized as oxygen deprivation, it may be too late to take effective action. The victim's motor skills deteriorate, making it difficult to operate emergency equipment or communicate with mission control. Their vision may become blurred or tunnel, and they may experience severe confusion or disorientation. Eventually, they lose consciousness and, without intervention, die from lack of oxygen. Carbon dioxide poisoning presents another form of suffocation that can occur in spacecraft. While the body is good at detecting high levels of carbon dioxide, the systems that remove this gas from the air can fail, leading to a gradual buildup that can be fatal. Carbon dioxide poisoning causes headaches, dizziness, shortness of breath, and eventually unconsciousness and death. The Apollo 13 mission provided a dramatic real-world example of how carbon dioxide buildup can threaten astronaut lives. When the spacecraft's main life support systems failed, the crew was forced to take refuge in the lunar module, which was designed to support 2 people for 2 days, not 3 people for 4 days. The carbon dioxide scrubbers in the lunar module became overloaded, and carbon dioxide levels began to rise to dangerous levels. Mission Control and the crew worked frantically to improvise a solution using duct tape, plastic bags, and parts from the command module to create makeshift carbon dioxide scrubbers. The fix worked, but for several tense hours, the crew faced the very real possibility of suffocating in their own exhaled breath. The incident highlighted just how dependent astronauts are on their life support systems and how quickly a malfunction can become life-threatening. Spacesuits present their own unique suffocation hazards. These portable life support systems must provide oxygen, remove carbon dioxide, and maintain pressure, all while being lightweight and allowing for mobility. A spacesuit is essentially a miniature spacecraft worn by a single person. And like spacecraft, they can fail in ways that can be fatal. One of the most terrifying scenarios for an astronaut performing a spacewalk is a failure of their suit's oxygen supply. Unlike in a spacecraft, where there might be time to don emergency oxygen masks or retreat to a safe area, a spacesuit failure during a spacewalk leaves the astronaut with only the air remaining in their suit. Depending on their level of activity and stress, this might be enough air for only a few minutes. During the Gemini program, astronaut Gene Cernan came dangerously close to suffocation during a spacewalk when his visor fogged up so severely that he could not see, and his exertion caused his suit's life support system to become overloaded. He was forced to struggle blindly back to the spacecraft while his heart rate soared and his oxygen consumption increased dramatically. Only quick action by his crewmate prevented what could have been a fatal suffocation. The psychological aspect of suffocation in space cannot be overlooked. The knowledge that you are completely dependent on mechanical systems for every breath creates a unique form of anxiety that can be overwhelming. Astronauts report being acutely aware of the sound of air circulation fans and oxygen generators, knowing that the silence of these systems could mean death. This psychological pressure is compounded by the fact that suffocation is a death that the victim experiences consciously, at least in the early stages. Unlike some other space-related deaths that cause rapid unconsciousness, suffocation allows the victim to remain aware of what is happening to them as their body slowly shuts down. The panic and terror associated with being unable to breathe can make the experience even more traumatic. Training for suffocation emergencies is a critical part of astronaut preparation. Candidates must learn to recognize the early symptoms of oxygen deprivation and practice emergency procedures until they become automatic. They train in altitude chambers, where they experience controlled hypoxia, so they can learn to recognize how their own bodies react to oxygen deprivation. Astronauts also practice emergency scenarios, where they must quickly don oxygen masks or retreat to emergency shelters within their spacecraft. These drills are conducted repeatedly because the margin for error is so small. In a real emergency, there may be only seconds to recognize the problem and take appropriate action before unconsciousness makes effective response impossible. The development of more reliable life support systems is an ongoing area of research and development. Engineers are working on systems that are more robust, easier to maintain, and less likely to fail. They are also developing better monitoring systems that can detect problems before they become life-threatening, giving astronauts more time to respond to emergencies. Future long-duration missions will place even greater demands on life support systems. A mission to Mars will require life support systems to function reliably for months or even years without the possibility of resupply from Earth. The failure of these systems would mean not just the loss of a mission, but the loss of human lives, with no possibility of rescue. The challenge is not just technical, but also psychological. Astronauts on long-duration missions must live with the constant knowledge that they are completely dependent on their life support systems for survival. They must maintain and monitor these systems while also carrying out their mission objectives, all while knowing that a single failure could mean suffocation and death. Research into closed-loop life support systems, which recycle air and water indefinitely, is critical for these future missions. These systems must be incredibly efficient and reliable, capable of supporting human life for years without outside input. They must also be maintainable by the crew, since there will be no possibility of getting replacement parts from Earth. The International Space Station serves as a testbed for many of these technologies. The station's life support systems have been continuously refined and improved over the years, providing valuable lessons about what works and what doesn't in the harsh environment of space. These lessons will be crucial for designing the life support systems that will keep astronauts alive during future missions to Mars and beyond. Despite all the technological advances and safety improvements, the threat of suffocation remains one of the most immediate and terrifying dangers facing astronauts. It is a reminder that in space, the most basic necessities of life must be artificially provided and maintained. The simple act of breathing, something that every human takes for granted on Earth, becomes a complex engineering challenge in the hostile environment of space. For those who choose to explore the cosmos, the battle against suffocation is a daily reality. Every breath they take is made possible by complex machinery and careful planning. Every malfunction or system failure brings with it the possibility of a slow, agonizing death as their bodies are deprived of the oxygen they need to survive. In the vast emptiness of space, the ability to breathe is not a given. It is a privilege that must be earned through careful engineering and constant vigilance. Spacecraft are among the most complex machines ever built by humanity, containing millions of components that must work together flawlessly in the most hostile environment imaginable. Every bolt, every wire, every computer chip must perform perfectly, because in space, there are no emergency services, no rescue teams, and no safe harbors. When a spacecraft malfunctions catastrophically, the results are almost always fatal, turning these marvels of engineering into death traps that hurtle through the void. The complexity of modern spacecraft is staggering. A typical spacecraft contains thousands of separate systems, each with its own components, sensors, and backup systems. These systems must work together seamlessly to maintain life support, provide power, control navigation, and communicate with Earth. The failure of any critical system can cascade into a complete breakdown that threatens the lives of everyone aboard. The most terrifying aspect of spacecraft malfunctions is how quickly they can escalate from minor problems to life-threatening emergencies. A small leak in a fuel line can lead to an explosion that destroys the entire vehicle. A computer glitch can cause the spacecraft to tumble out of control, making it impossible to maintain proper orientation for solar panels or communication antennas. A failure in the electrical system can knock out life support, leaving the crew with only the air remaining in their suits. Perhaps the most devastating type of spacecraft malfunction is explosive decompression, where the pressurized hull of the spacecraft is suddenly breached, allowing all the air inside to rush out into the vacuum of space. This can happen due to impact with space debris, metal fatigue, or the failure of a seal or hatch. When it occurs, the results are immediate and catastrophic. During explosive decompression, the air inside the spacecraft rushes toward the breach with tremendous force. The pressure difference between the inside of the spacecraft and the vacuum of space creates winds that can reach hurricane force within seconds. Anything not securely fastened, including crew members, can be sucked toward the breach and potentially ejected into space. The Soyuz 11 tragedy in 1971 provides a stark example of how explosive decompression can kill. During the spacecraft's return to Earth, a valve malfunctioned and opened prematurely, causing the cabin to depressurize at an altitude of over 100 miles. The 3 cosmonauts aboard were not wearing pressure suits, and they had no time to don emergency equipment before the cabin pressure dropped to fatal levels. The crew of Soyuz 11 died within seconds of the decompression event. When the spacecraft was recovered, the cosmonauts were found still strapped in their seats, with no obvious signs of injury. They had simply suffocated as the air rushed out of their spacecraft and into the void. The tragedy led to major changes in spacecraft design and procedures, but it remains a stark reminder of how quickly a simple malfunction can become fatal. Fire represents another catastrophic threat in the confined environment of a spacecraft. On Earth, Fires consume oxygen and produce smoke and toxic gases, but gravity helps to carry these byproducts away from the fire and allows people to escape to safety. In the microgravity environment of space, fire behaves very differently and can be far more dangerous. In microgravity, hot gases and smoke do not rise as they do on Earth. Instead, they tend to remain near the fire, creating a concentrated cloud of toxic fumes that can quickly fill the entire spacecraft. The lack of gravity also means that burning particles and droplets of molten material can float freely through the cabin, potentially igniting other materials and spreading the fire rapidly. The oxygen-rich atmosphere inside most spacecraft makes fires burn hotter and faster than they would on Earth. While Earth's atmosphere contains about 21% oxygen, spacecraft often maintain higher oxygen concentrations to reduce the total cabin pressure, while still providing adequate oxygen for the crew. This oxygen-rich environment can cause materials that are normally fire-resistant to burn rapidly and intensely. The Apollo 1 fire in 1967 demonstrated just how deadly spacecraft fires can be. During a ground test, a spark ignited materials inside the command module, which was pressurized with pure oxygen at higher than normal pressure. The fire spread with incredible speed, consuming the cabin interior in seconds. The 3 astronauts inside, Gus Grissom, Ed White, and Roger Chaffee, were trapped and died from smoke inhalation and burns before they could escape. The Apollo 1 tragedy was made worse by the spacecraft's inward opening hatch, which could not be opened against the pressure created by the expanding hot gases from the fire. The astronauts struggled desperately to open the hatch as the fire consumed their spacecraft, but they were defeated by the very design that was meant to keep them safe. Their deaths led to major redesigns of the Apollo spacecraft and changes in procedures that likely saved the lives of future astronauts. Electrical system failures represent another category of catastrophic spacecraft malfunction. Modern spacecraft are entirely dependent on electrical power for everything from life support to navigation to communication with Earth. A major electrical failure can leave a spacecraft dead in space, with no way to maintain life support or control its trajectory. The most common cause of electrical system failure is damage to the spacecraft's solar panels or batteries. Solar panels can be damaged by micrometeoroids, space debris, or simply by the harsh environment of space. Batteries can fail due to manufacturing defects, overcharging, or the extreme temperature cycles experienced in space. When these power sources fail, the spacecraft begins a race against time to restore power before critical systems shut down. The Apollo 13 mission provides a dramatic example of how electrical system failures can threaten crew survival. When an oxygen tank exploded, it damaged the spacecraft's electrical system and forced the crew to shut down most of the command module's systems to conserve power. The astronauts were forced to use the lunar module as a lifeboat, but even its limited power reserves were stretched to the breaking point during the 4-day journey back to Earth. Navigation system failures can be equally deadly, especially for spacecraft traveling to distant destinations. If a spacecraft loses the ability to determine its position and orientation, it can drift off course and become lost in space. Without proper navigation, the spacecraft cannot point its antennas toward Earth for communication, cannot orient its solar panels toward the sun for power, and cannot fire its engines in the right direction to correct its trajectory. The loss of navigation capability can turn a routine mission into a one-way trip to nowhere. A spacecraft that drifts off course may be impossible to locate and rescue, leaving the crew to slowly die as their life support systems fail and their supplies run out. The vast distances involved in space travel mean that even small navigation errors can result in missing the target by millions of miles. Communication system failures create their own unique form of terror. When a spacecraft loses contact with Earth, the crew becomes completely isolated, cut off from the support and expertise of mission control. They must rely entirely on their own knowledge and resources to solve any problems that arise, with no possibility of getting help or advice from the ground. The psychological impact of losing communication with Earth cannot be overstated. Astronauts describe the comfort they get from being able to talk to mission control, knowing that there are hundreds of people on the ground working to support their mission and keep them safe. When that link is severed, the crew must face the hostile environment of space alone, knowing that no one on Earth even knows whether they are alive or dead. Structural failures represent perhaps the most catastrophic type of spacecraft malfunction. These occur when the physical structure of the spacecraft breaks apart due to stress, metal fatigue, or impact damage. Unlike other types of failures, which may leave the crew with some time to respond or work around the problem, structural failures are usually immediate and fatal. The Space Shuttle Challenger disaster in 1986 was caused by a structural failure in one of the solid rocket boosters. A faulty seal allowed hot gases to escape and burn through the external fuel tank, causing the entire vehicle to break apart just 73 seconds after launch. The crew compartment remained intact during the breakup, but the astronauts likely survived the initial explosion, only to die when their cabin hit the ocean surface at high speed. The Columbia disaster in 2003 was also caused by a structural failure, though it occurred during re-entry rather than launch. A piece of foam insulation had struck the leading edge of the shuttle's wing during launch, creating a hole that allowed superheated gases to enter the wing structure during re-entry. The wing eventually failed, causing the shuttle to break apart and killing all 7 crew members. These disasters highlight the unforgiving nature of space travel, where even small defects or minor damage can lead to catastrophic failure. The extreme conditions of launch and re-entry place enormous stresses on spacecraft structures, and any weakness can prove fatal when those stresses are applied. Computer system failures have become increasingly dangerous as spacecraft have become more dependent on automated systems. Modern spacecraft rely on computers for everything from navigation to life support control to communication with Earth. A major computer failure can leave the crew unable to control their spacecraft or even to understand what is happening to their systems. The most frightening aspect of computer failures is that they can cause multiple systems to fail simultaneously. A single computer often controls many different spacecraft functions, so when it fails, the crew may suddenly find themselves dealing with problems in navigation, life support, communication, and power systems all at the same time. This can quickly overwhelm even the most experienced astronauts. Software bugs represent a particularly insidious form of computer failure because they may not manifest until the spacecraft is already in space and facing critical situations. A bug in the navigation software might not cause problems during normal flight, but could prove fatal during a critical maneuver. A flaw in the life support control software might work fine under normal conditions, but fail when the system is stressed or damaged. The increasing complexity of spacecraft systems means that catastrophic failures are becoming more likely, not less. Each new system adds potential failure points, and the interactions between systems can create unexpected failure modes that are difficult to predict or test on the ground. Engineers work constantly to identify and eliminate these potential failures, but the complexity of modern spacecraft means that some risks will always remain. Redundancy is the primary defense against catastrophic spacecraft failures. Critical systems are usually duplicated or even triplicated so that if one system fails, backup systems can take over. But redundancy adds weight, complexity, and cost to spacecraft, and it is not always possible to provide backups for every system. Even when backup systems exist, they can fail too, or the same event that damages the primary system can damage the backups as well. The human factor in spacecraft failures cannot be ignored. Astronauts are highly trained professionals, but they are still human, and humans make mistakes. A simple error in operating a switch or entering a command can cascade into a catastrophic failure. The stress and fatigue of space travel can increase the likelihood of human error, especially during long-duration missions. Training and simulation are crucial for preparing astronauts to deal with spacecraft malfunctions. Crews spend hundreds of hours practicing emergency procedures in simulators that can replicate almost any conceivable failure scenario. They learn to work together as a team under extreme stress, making quick decisions with incomplete information while their lives hang in the balance. But no amount of training can prepare for every possible failure mode. Spacecraft are so complex that new failure scenarios are constantly being discovered, both through analysis and through actual failures in space. Each mission provides new lessons about what can go wrong and how to prevent it. But the learning process comes at a terrible cost when those lessons are learned through the loss of human life. The future of space exploration will bring even more complex spacecraft designed for longer missions to more distant destinations. These vehicles will need to operate reliably for years without the possibility of repair or resupply from Earth. The potential for catastrophic failure will only increase as these systems become more complex and operate for longer periods in the harsh environment of space. Despite all the risks and the tragic losses that have occurred, humans continue to venture into space in ever more sophisticated spacecraft. Each mission represents a calculated risk, a bet that human ingenuity and engineering can overcome the hostile environment of space. Sometimes that bet pays off, and explorers return safely to Earth with new knowledge and achievements. But sometimes the bet fails, and spacecraft become tombs that carry their crews into the infinite darkness of space. The story of spacecraft malfunctions is ultimately a story of human ambition confronting the unforgiving realities of space travel. It is a reminder that for all our technological achievements, we are still fragile beings venturing into an environment that was never meant to sustain human life. Every successful mission is a triumph over the countless things that can go wrong, and every failure is a sobering reminder of the price we pay for pushing the boundaries of human exploration. Space may appear to be an endless void of nothingness, but in reality, it has become a dangerous highway, filled with debris traveling at unimaginable speeds. What was once a pristine frontier has become cluttered with the remnants of more than 60 years of space exploration, creating an invisible minefield that poses a constant threat to any spacecraft or astronaut venturing beyond Earth's atmosphere. The problem of space debris began with the very first artificial satellite, Sputnik 1, launched by the Soviet Union in 1957. Since then, thousands of rockets have been launched, carrying satellites, space probes, and crewed missions into orbit and beyond. Each launch leaves behind debris, from spent rocket stages to fragments of exploded satellites, all of which continues to orbit Earth at tremendous speeds. Today, scientists estimate that there are more than 130 million pieces of space debris larger than 1 millimeter orbiting Earth. Of these, approximately 34,000 pieces are larger than 10 centimeters and are actively tracked by ground-based radar systems. But it is the smaller pieces, the ones too small to track reliably, that pose the greatest danger to human life in space. The destructive potential of space debris comes not from its size, but from its incredible velocity. Objects in low Earth orbit travel at speeds of approximately 17,500 miles per hour. At these velocities, even the tiniest piece of debris becomes a deadly projectile capable of puncturing spacecraft hulls, destroying critical systems, or killing astronauts. To understand the destructive power of high-speed impacts in space, consider that a paint fleck traveling at orbital velocity carries the same kinetic energy as a small caliber bullet fired from a gun. A piece of debris the size of a marble has the energy of a hand grenade. Larger pieces, such as fragments from exploded satellites or spent rocket stages, carry enough energy to completely destroy a spacecraft upon impact. The invisibility of most space debris makes it particularly terrifying. Unlike aircraft flying through crowded airspace, where pilots can see other planes and air traffic controllers can guide them to safety, spacecraft must navigate through clouds of debris that are largely invisible and unpredictable. Most debris pieces are too small to be detected by ground-based tracking systems, yet they are large enough to cause catastrophic damage. The speed at which space debris travels means that there is virtually no warning when an impact is about to occur. Even if a piece of debris were detected heading toward a spacecraft, there would typically be insufficient time to maneuver out of the way. The impact occurs so quickly that it is over before anyone aboard the spacecraft can even realize what has happened. When space debris strikes a spacecraft, the results depend on the size and speed of the impacting object and where it hits. A small piece of debris might only create a tiny hole in the spacecraft's hull, causing a slow leak that could be detected and repaired. But a larger piece can punch straight through the spacecraft, creating massive holes that cause explosive decompression and almost certain death for anyone aboard. The International Space Station has been struck by space debris numerous times during its operational life. Most of these impacts have been by very small particles that create tiny craters in the station's exterior surfaces or small holes in its solar panels. But even these minor impacts serve as constant reminders of the debris threat, and larger impacts that could prove catastrophic are always a possibility. In 2009, the crew of the International Space Station was forced to take shelter in their Soyuz escape capsules when a piece of space debris was detected on a collision course with the station. The debris, a fragment from a satellite that had been destroyed in an anti-satellite weapon test, passed close enough to the station that mission controllers were genuinely concerned about a catastrophic impact. The threat of debris impact is not limited to large spacecraft like the International Space Station. Astronauts performing spacewalks are particularly vulnerable because they have no protection other than their spacesuits. A piece of debris that might only cause minor damage to a spacecraft could easily puncture a spacesuit and kill the astronaut inside. During spacewalks, astronauts are acutely aware of the debris threat. They know that at any moment, a piece of debris too small to see could strike them with the force of a bullet. This knowledge creates a constant undercurrent of anxiety that can make even routine tasks more difficult and stressful. The psychological pressure of knowing that death could come without warning from an invisible source is unlike any other hazard faced by humans. The problem of space debris is getting worse, not better. Each new launch adds more debris to the growing cloud of objects orbiting Earth. When satellites reach the end of their operational lives, they often break apart due to collisions with other debris or explosions caused by residual fuel or battery failures. Each breakup event creates thousands of new debris fragments, exponentially increasing the overall debris population. The phenomenon known as the Kessler syndrome represents the ultimate nightmare scenario for space debris. Named after NASA scientist Donald Kessler, who first described it in 1978, this scenario describes a cascade of collisions where each impact creates more debris, which in turn causes more collisions, creating an exponentially growing cloud of debris that makes space travel impossible. In 2009, a collision between an active communications satellite and a defunct Russian military satellite provided a real-world example of how quickly the debris problem can escalate. The collision occurred at a relative speed of over 25,000 miles per hour and created more than 2,000 trackable pieces of debris, along with countless smaller fragments that cannot be tracked but are still dangerous. The Chinese anti-satellite weapon test in 2007 made the debris problem significantly worse by deliberately destroying a satellite and creating more than 3,000 pieces of trackable debris. This single event increased the overall debris population by more than 10% and created a debris cloud that will remain dangerous for decades to come. Military activities in space have contributed significantly to the debris problem. Several nations have conducted anti-satellite weapon tests that have created massive amounts of debris. These tests are typically conducted using kinetic kill vehicles that destroy the target satellite by ramming into it at high speed, creating thousands of debris fragments that spread throughout the target's orbital region. The debris created by these weapons tests poses a threat not just to military satellites, but to all spacecraft operating in the affected orbital regions. The debris does not discriminate between military and civilian targets, and pieces created by weapons tests have forced the International Space Station to perform avoidance maneuvers and have threatened other peaceful space missions. Natural meteoroids also contribute to the space debris problem, though to a much lesser extent than human-made debris. These cosmic dust particles and small rocks travel through space at speeds that can exceed 40 miles per second, making them extremely dangerous despite their small size. While the Earth's atmosphere protects us from most meteoroids, spacecraft operating in space have no such protection. The Leonid meteor shower, which occurs annually in November, creates periods of increased meteoroid activity that can pose additional risks to spacecraft. During peak years, the rate of meteoroid impacts can increase dramatically, forcing mission planners to schedule critical activities to avoid these high-risk periods. Spacecraft designers have developed various strategies to protect against debris impacts, but none of these approaches can provide complete protection. Whipple shields, named after astronomer Fred Whipple, use multiple layers of material spaced apart to break up incoming debris and distribute its energy over a larger area. These shields can protect against small debris, but they add weight and complexity to spacecraft design. The problem with protective shielding is that it cannot be made strong enough to stop large pieces of debris without making the spacecraft prohibitively heavy and expensive. The amount of shielding required to stop a piece of debris the size of a softball would make most spacecraft impossible to launch. Instead, designers must accept that some risks cannot be eliminated and focus on protecting the most critical systems and crew areas. Tracking and cataloging space debris is a continuous effort that involves radar and optical telescopes around the world. The United States Space Surveillance Network tracks objects larger than about 10 centimeters in low Earth orbit, maintaining a catalog of known debris that can be used to predict potential collisions. When a collision threat is identified, spacecraft can sometimes perform avoidance maneuvers to reduce the risk of impact. But tracking has its limitations. Smaller pieces of debris cannot be reliably detected and tracked, yet they are still large enough to cause significant damage. The orbital mechanics of space debris are also complex, with objects' paths affected by atmospheric drag, solar radiation pressure, and gravitational perturbations that make long-term predictions difficult. The International Space Station regularly performs debris avoidance maneuvers when tracking data indicates a potential collision. These maneuvers involve firing the station's thrusters to slightly change its orbit and avoid the predicted impact. But these maneuvers consume fuel and disrupt station operations, and they can only be performed when sufficient warning is available. When avoidance maneuvers are not possible, the station crew must take shelter in their Soyuz spacecraft, ready to evacuate if a catastrophic impact occurs. These shelter procedures are practiced regularly, but the knowledge that they may need to abandon their home in space at a moment's notice creates constant psychological stress for the crew. The growing debris problem is forcing changes in how spacecraft are designed and operated. New satellites are being designed with propulsion systems that allow them to deorbit at the end of their operational lives, preventing them from becoming long-term debris. Mission planners are also working to reduce the amount of debris created during launches by ensuring that rocket stages and other components either return to Earth or are placed in disposal orbits. International efforts to address the space debris problem include guidelines for responsible space activities and research into active debris removal technologies. Some proposed solutions involve using robotic spacecraft to capture and deorbit large pieces of debris, while others suggest using lasers to alter debris trajectories or break up larger pieces into smaller fragments that would burn up in the atmosphere more quickly. Despite these efforts, the space debris problem will likely get worse before it gets better. The debris already in orbit will remain dangerous for decades or centuries, depending on their altitude. New launches continue to add to the problem, and the commercial space industry is growing rapidly, with plans for thousands of new satellites in the coming years. The psychological impact of the debris threat extends beyond the immediate danger to astronauts and spacecraft. The knowledge that humanity has polluted space with dangerous debris creates a sense of guilt and responsibility among those involved in space exploration. What was once seen as an infinite frontier is now recognized as a finite resource that must be carefully managed to remain usable for future generations. For astronauts, the constant threat of debris impact creates a unique form of stress that is difficult to manage. Unlike other space hazards that can be controlled or predicted to some extent, debris impacts are largely random events that can occur without warning. This uncertainty makes it impossible to fully relax or feel safe, even during routine activities. The debris threat also affects mission planning and operations in ways that limit what can be accomplished in space. Critical activities must sometimes be postponed due to debris conjunctions, and spacecraft must be designed with additional shielding that reduces their payload capacity and increases their cost. The freedom to operate in space is being steadily eroded by the growing cloud of debris that surrounds our planet. Future missions to Mars and other destinations will face debris threats not just near Earth, but potentially throughout the solar system. While interplanetary space is generally much cleaner than Earth orbit, it still contains natural meteoroids and the debris from previous space missions. As human activities expand beyond Earth orbit, we risk creating debris problems in other regions of space as well. The story of space debris is ultimately a cautionary tale about the unintended consequences of human activity. What began as humanity's greatest adventure, the exploration of space, has created an invisible threat that now endangers all future space activities. The debris orbiting Earth serves as a reminder that even in the vastness of space, our actions have consequences that can affect generations of future explorers. In the silent void between Earth and the stars, millions of pieces of debris continue their endless orbits, waiting to encounter the next spacecraft or astronaut unlucky enough to cross their path. Each piece represents a potential death sentence, a random event that could end a mission or a life in an instant. For those who venture into space, the invisible danger of debris impacts serves as a constant reminder that even the emptiest places in the universe can be filled with deadly threats. While the physical dangers of space exploration are well documented and understood, the psychological threats faced by astronauts are equally real and potentially just as deadly. The human mind, evolved to function in the familiar environment of Earth, can be pushed to its breaking point by the isolation, confinement, and stress of space travel. In the vast emptiness of space, psychological breakdown can be as fatal as any mechanical failure. The isolation experienced in space is unlike anything that exists on Earth. Even in the most remote locations on our planet, there is still the knowledge that other humans are relatively nearby, and that rescue is at least theoretically possible. In space, astronauts are separated from the rest of humanity by hundreds or thousands of miles of vacuum, with no possibility of immediate rescue if something goes wrong. This isolation is made more profound by the visual reminder of just how far from home they really are. When astronauts look out the window of their spacecraft, they see the infinite blackness of space stretching in all directions. Earth, if it is visible at all, appears as a small blue dot suspended in the darkness. This perspective can be both awe-inspiring and terrifyingly lonely. driving home the reality that they are truly alone in an environment that is fundamentally hostile to human life. The psychological impact of this isolation can manifest in many ways. Some astronauts report feeling a profound sense of loneliness and disconnection from humanity. Others experience what psychologists call the overview effect, a cognitive shift toward greater environmental awareness and a sense of unity with all life on Earth. But for some, the isolation can lead to depression, anxiety, and in extreme cases, complete psychological breakdown. Confinement adds another layer of psychological stress to space missions. Spacecraft are necessarily small and cramped, with every cubic inch of space at a premium. Astronauts must live and work in these confined spaces for weeks, months, or potentially years, with no opportunity to step outside for fresh air or to experience the freedom of open spaces. The International Space Station, while large by spacecraft standards, still provides less living space than a typical apartment. Yet it must house multiple crew members for months at a time. Every surface serves multiple purposes, and there is virtually no private space where astronauts can retreat when they need solitude. The constant presence of crewmates, combined with the inability to leave the confined environment, can create interpersonal tensions that would be manageable under normal circumstances, but become overwhelming in space. The effects of prolonged confinement on the human psyche are well documented from studies of submarines, polar research stations, and prisons. People confined in small spaces for extended periods often experience claustrophobia, irritability, and difficulty concentrating. They may become hypersensitive to minor annoyances, leading to conflicts with others who share their confined space. In the worst cases, confinement can trigger panic attacks, violent outbursts, or complete mental breakdown. The constant noise inside spacecraft adds to the psychological stress of confinement. Life support systems, computers, and other equipment create a continuous background of humming, clicking, and whirring sounds that never stop. Unlike on Earth, where people can escape to quiet spaces, astronauts must endure this constant noise throughout their entire mission. The inability to find silence can become maddening over time, contributing to stress, insomnia, and psychological instability. Sleep disruption is another major psychological threat in space. The human circadian rhythm, which regulates sleep and wake cycles, is synchronized to Earth's 24-hour day-night cycle. In space, this natural rhythm is disrupted by the artificial lighting of the spacecraft and, for those in Earth orbit, by the rapid cycle of sunrises and sunsets that occur every 90 minutes. Astronauts often struggle to maintain normal sleep patterns, leading to chronic sleep deprivation that affects their cognitive function, emotional stability, and decision-making ability. Sleep deprivation can cause hallucinations, paranoia, and impaired judgment, all of which can be dangerous in the high-risk environment of space. The psychological effects of poor sleep are compounded by the stress of the mission and the knowledge that clear thinking is essential for survival. The absence of familiar sensory experiences can also take a psychological toll. In space, there are no natural sounds like wind, rain, or birdsong. There are no natural smells like flowers, ocean air, or fresh earth. The sense of taste can be altered by the effects of microgravity, making food less appealing and potentially contributing to poor nutrition. These sensory deprivations can contribute to a sense of unreality and disconnection from normal human experience. Microgravity itself creates psychological challenges beyond its physical effects on the body. The constant floating sensation can be disorienting and uncomfortable, especially for astronauts who are prone to motion sickness. The inability to feel weight or to have a consistent sense of up and down can create a persistent feeling of being off balance or out of control. The lack of gravity also affects how astronauts interact with their environment. Simple tasks that are automatic on Earth become complex and frustrating in microgravity. Objects float away if not secured. Liquids form spheres that can be difficult to manage, and movement requires careful planning to avoid bumping into surfaces or equipment. This constant need to consciously control interactions with the environment can be mentally exhausting. The extreme workload and responsibility carried by astronauts create additional psychological pressure. Every astronaut knows that their mission costs millions or billions of dollars and represents years of planning and preparation by thousands of people. The weight of this responsibility, combined with the knowledge that mistakes can be fatal, creates a level of stress that few people on Earth ever experience. Astronauts must maintain peak performance levels while dealing with complex technical tasks, emergency procedures, and scientific experiments. They must do this while coping with all the other psychological stresses of space travel, from isolation to confinement to sleep disruption. The pressure to perform flawlessly under these conditions can push even the most psychologically robust individuals to their breaking point. The fear of death, while often suppressed or managed through training and professionalism, is a constant presence in the minds of astronauts. They know that they are operating in an environment where small mistakes can be fatal and where rescue may be impossible. This knowledge can create a persistent background anxiety that affects sleep, concentration, and emotional well-being. Different people cope with this fear in different ways. Some astronauts become hypervigilant, constantly checking and rechecking systems and procedures in an attempt to control every possible risk. Others may develop a fatalistic attitude, accepting that death is a possibility and trying not to think about it. Both approaches can be psychologically unhealthy if taken to extremes. Communication delays add another dimension to the psychological challenges of space travel. While astronauts in Earth orbit can communicate with mission control in real time, those traveling to more distant destinations face increasingly long delays in communication. A mission to Mars would involve communication delays of up to 24 minutes each way, making real-time conversation impossible. These communication delays can make astronauts feel even more isolated and cut off from Earth. The inability to have normal conversations with friends, family, or mission control can be deeply frustrating and can contribute to feelings of loneliness and disconnection. In emergency situations, the knowledge that help and advice are minutes or hours away can create additional stress and anxiety. The psychological effects of space travel can be cumulative, building over time until they reach a breaking point. An astronaut who copes well with the first few weeks or months of a mission may gradually deteriorate as the psychological stresses continue to accumulate. This makes long-duration missions particularly challenging, as crew members may appear to be functioning normally, even as their psychological state slowly deteriorates. Cultural and interpersonal conflicts can become magnified in the confined, stressful environment of space. Astronauts from different countries may have different communication styles, work habits, or cultural expectations that can lead to misunderstandings and conflicts. These conflicts, which might be minor annoyances on Earth, can become major sources of stress when there is no escape from the other person, and when teamwork is essential for survival. The selection and training of astronauts includes extensive psychological screening and preparation, but it is impossible to predict exactly how someone will react to the unique stresses of space travel. Some people who appear psychologically robust on Earth may struggle in space, while others who seem more fragile may adapt surprisingly well. This unpredictability makes psychological breakdown a constant risk that must be carefully monitored and managed. Space agencies have developed various strategies for managing the psychological health of astronauts. These include regular psychological evaluations, structured communication with family and friends on Earth, recreational activities and entertainment, and careful attention to crew dynamics and interpersonal relationships. But despite these precautions, the risk of psychological problems remains significant. The use of psychiatric medications in space presents its own challenges. Many medications behave differently in the microgravity environment, and the confined space of a spacecraft makes it difficult to manage serious psychiatric emergencies. An astronaut experiencing a complete psychological breakdown could pose a danger not only to themselves, but to their crewmates and the mission as a whole. Historical examples of psychological problems in space are relatively rare, partly because space agencies are reluctant to discuss such incidents publicly. However, there have been reports of astronauts experiencing depression, anxiety, and interpersonal conflicts during long-duration missions. The Soviet space program reportedly had several incidents where cosmonauts experienced psychological problems that affected their ability to function effectively. One well-documented case involved cosmonaut Valery Ryumin, who experienced significant psychological stress during a long-duration mission to the Salyut space station. He reported feeling increasingly isolated and depressed as the mission progressed, and his relationship with his crewmate became strained to the point where they barely spoke to each other. While both cosmonauts completed the mission successfully, the incident highlighted the importance of psychological factors in long-duration space travel. The future of space exploration will involve even longer missions to more distant destinations, making psychological health an even more critical concern. A mission to Mars would last at least 18 months, including the journey to Mars, time on the planet's surface, and the return trip to Earth. During this time, the crew would be completely isolated from Earth, with no possibility of rescue or resupply. The psychological challenges of such a mission would be unprecedented. The crew would need to maintain their mental health and work effectively together for far longer than any previous space mission. They would need to cope with the stress of landing on an alien world, conducting complex scientific operations, and then successfully launching from Mars for the long journey home. Research into the psychological aspects of long-duration space travel is ongoing, with studies conducted in simulated space environments on Earth. These studies have revealed important insights into how people cope with isolation, confinement, and stress over extended periods. However, the unique environment of space, with its microgravity, radiation exposure, and genuine life-threatening dangers, cannot be fully replicated on Earth. The development of virtual reality and advanced communication technologies may help address some of the psychological challenges of future space missions. Virtual reality could allow astronauts to experience simulated Earth environments, potentially reducing feelings of isolation and sensory deprivation. Better communication systems could reduce delays and allow for more natural interactions with people on Earth. However, technology alone cannot solve the fundamental psychological challenges of space travel. The human mind will always struggle with the isolation, confinement, and stress of operating in an environment that is fundamentally hostile to life. The success of future long-duration missions will depend not just on advanced technology and careful planning, but on a deep understanding of human psychology and the development of effective strategies for maintaining mental health in space. The psychological dangers of space travel serve as a reminder that human beings are not just physical entities that need air, water, and food to survive. We are also psychological beings who need social connection, sensory stimulation, and a sense of purpose and meaning. In the hostile environment of space, these psychological needs can be just as critical for survival as any physical requirement. For those who choose to venture into the cosmos, the battle for psychological survival is as important as the fight against vacuum, radiation, and mechanical failure. The human mind, pushed to its limits by the stresses of space travel, can become either the greatest asset or the deadliest threat that astronauts face. In the vast emptiness of space, maintaining one's sanity may be the ultimate challenge, and psychological breakdown may prove to be the most insidious and dangerous way to die among the stars. While the immediate dangers of space travel capture our attention with their dramatic and terrifying nature, there is another category of threats, that work more slowly and insidiously. The long-term effects of space travel on the human body represent a form of slow death, where the very act of living in space gradually breaks down the biological systems that keep us alive. These effects may not kill astronauts during their missions, but they can rob them of their health and vitality for years or decades after they return to Earth. The human body evolved over millions of years to function in Earth's specific environment. Every system, from our bones and muscles to our cardiovascular and nervous systems, developed under the constant influence of Earth's gravity, magnetic field, and atmospheric protection. When we remove these fundamental environmental factors, as we do in space travel, the body begins to change in ways that can be both surprising and alarming. Bone loss represents one of the most serious long-term effects of space travel. On Earth, our bones are constantly being broken down and rebuilt in a process called bone remodeling. This process is stimulated by the mechanical stress that gravity places on our skeletal system through weight-bearing activities like walking, running, and simply standing upright. In the microgravity environment of space, this mechanical stress is largely eliminated, and the body responds by reducing bone density. Astronauts lose bone mass at a rate of approximately 1 to 2% per month during space missions. This may not sound like much, but over the course of a long mission, the cumulative loss can be devastating. A 6-month mission to the International Space Station can result in a 10 to 20% loss of bone density in weight-bearing bones like the hips and spine. This level of bone loss is equivalent to what a postmenopausal woman might experience over 10 to 20 years. The bone loss experienced by astronauts is not evenly distributed throughout the skeleton. The bones that normally bear the most weight on Earth, such as the femur, pelvis, and vertebrae, experience the greatest loss. These are also the bones most critical for mobility and structural support, making their deterioration particularly problematic for astronauts returning to Earth's gravitational environment. The process of bone loss in space is not just about losing calcium and other minerals. The actual structure of the bone tissue changes, becoming more porous and fragile. The trabecular bone, which forms the internal scaffolding that gives bones their strength, becomes thinner and more widely spaced. This structural deterioration cannot be easily reversed, even with intensive rehabilitation after returning to Earth. When astronauts return from long-duration missions, they face a significantly increased risk of fractures and other bone-related injuries. Simple activities that would pose no risk to a healthy person, such as running or playing sports, can become dangerous for astronauts whose bones have been weakened by space travel. Some astronauts have experienced fractures from relatively minor incidents that would not have injured them before their space missions. The recovery of bone density after space travel is a slow and incomplete process. While some bone mass can be regained through exercise and medication, studies suggest that astronauts may never fully recover the bone density they had before their missions. This permanent loss of bone strength represents a lifelong legacy of their time in space, potentially affecting their mobility and quality of life for decades to come. Muscle atrophy is another major long-term effect of space travel that can have lasting consequences for astronauts' health. In the microgravity environment of space, muscles do not need to work against gravity to maintain posture or to move the body around. Without this constant mechanical stress, muscles begin to weaken and shrink at an alarming rate. The effects of muscle atrophy in space are most pronounced in the anti-gravity muscles, those that normally work to keep us upright against Earth's gravitational pull. These include the muscles of the back, legs, and core that are essential for walking, standing, and maintaining good posture. Astronauts can lose up to 20% of their muscle mass during a 6-month mission, with some muscles shrinking even more dramatically. The loss of muscle mass is accompanied by changes in muscle fiber composition. The slow twitch muscle fibers that provide endurance and postural support are particularly affected, being replaced by fast twitch fibers that are better suited for quick, powerful movements, but less effective for sustained activity. This change in muscle composition can affect an astronaut's stamina and endurance long after they return to Earth. Cardiovascular deconditioning is another serious long-term consequence of space travel. On Earth, the cardiovascular system must work against gravity to pump blood from the legs back to the heart and to maintain proper blood pressure when standing upright. In microgravity, these challenges are eliminated, and the cardiovascular system begins to adapt to the easier conditions. The heart muscle itself can weaken during space missions, becoming less efficient at pumping blood. The total blood volume decreases as the body sheds what it perceives as excess fluid. The walls of blood vessels become less elastic, and the body loses some of its ability to regulate blood pressure in response to changes in position or activity level. When astronauts return to Earth, their weakened cardiovascular systems struggle to readapt to gravity's demands. Many experience orthostatic intolerance, a condition where standing upright causes dizziness, fainting, or rapid heart rate as the cardiovascular system fails to maintain adequate blood flow to the brain. This condition can persist for weeks or months after returning from space, limiting astronauts' ability to perform normal activities. The effects of radiation exposure during space travel represent perhaps the most insidious long-term threat to astronaut health. Unlike the other effects we have discussed, which are primarily caused by microgravity, radiation damage accumulates throughout a space mission and can continue to cause problems for years or decades after the astronaut returns to Earth. The increased cancer risk associated with space radiation exposure is well established, but the exact magnitude of this risk remains uncertain. Current estimates suggest that a 6-month mission to the International Space Station increases an astronaut's lifetime cancer risk by approximately 3%. For longer missions, such as a journey to Mars, this risk could be much higher, potentially increasing an astronaut's cancer risk by 10% or more. The types of cancer most associated with radiation exposure include leukemia, lung cancer, breast cancer, and cancers of the digestive system. These cancers may not appear for years or decades after the radiation exposure, making it difficult to establish direct causal relationships. However, studies of atomic bomb survivors and nuclear workers have provided clear evidence that even relatively low levels of radiation exposure can significantly increase cancer risk. Radiation exposure can also affect the central nervous system in ways that may not become apparent until years after a space mission. Some studies suggest that cosmic radiation exposure can accelerate cognitive aging, potentially leading to earlier onset of dementia or other neurodegenerative conditions. The high-energy particles that make up cosmic radiation can damage brain cells and neural pathways in ways that may have lasting consequences for cognitive function. The effects of space travel on the immune system represent another area of concern for long-term astronaut health. The stress of space travel, combined with radiation exposure and other factors, can suppress immune function and make astronauts more susceptible to infections and diseases. Some studies have found that astronauts show signs of immune suppression that can persist for months after returning from space. This immune suppression may increase the risk of developing cancers, autoimmune diseases, and other conditions that depend on proper immune system function. The long-term consequences of this immune dysfunction are not yet fully understood, but they represent a potentially serious threat to astronaut health that may not become apparent until years after their space missions. Vision problems have emerged as an unexpected long-term consequence of space travel that affects a significant percentage of astronauts. The condition, known as spaceflight-associated neuroocular syndrome, or SANS, involves changes in vision that can include nearsightedness, farsightedness, and other visual disturbances. The exact cause of SANS is not fully understood, but it appears to be related to changes in intracranial pressure caused by fluid shifts in microgravity. The optic nerve can become swollen, and the shape of the eyeball can change, leading to permanent alterations in vision. Some astronauts have experienced vision changes that persist for years after their return to Earth, requiring corrective lenses or other interventions. The psychological impact of these long-term health effects cannot be understated. Astronauts who return from space missions, knowing that their bodies have been permanently altered by the experience, may struggle with depression, anxiety, and concerns about their future health. The knowledge that they may face increased cancer risks, bone fractures, or other health problems for the rest of their lives can be a heavy psychological burden. The social and family impacts of these health effects can also be significant. Astronauts may find themselves unable to participate in physical activities they once enjoyed, or they may require ongoing medical care and monitoring for potential health problems. The financial costs of long-term medical care can be substantial, and the emotional toll on family members who must watch their loved ones deal with the consequences of space travel can be considerable. Current research efforts are focused on understanding these long-term effects better and developing countermeasures to prevent or minimize them. Exercise programs during space missions have proven effective at reducing some of the muscle and bone loss, but they cannot completely prevent these changes. Pharmaceutical interventions, such as bisphosphonate drugs to prevent bone loss, are being studied, but come with their own potential side effects. Artificial gravity, generated by rotating spacecraft, represents a potential solution to many of the long-term health effects of space travel. By creating a gravitational environment similar to Earth's, rotating spacecraft could maintain the mechanical stresses needed to preserve bone and muscle mass and maintain normal cardiovascular function. However, the engineering challenges of building large rotating spacecraft are significant, and such vehicles would be much more complex and expensive than current spacecraft designs. The development of better radiation shielding is another active area of research, as reducing radiation exposure during space missions could significantly decrease the long-term cancer risk faced by astronauts. However, effective radiation shielding is heavy and expensive, and current technology cannot provide complete protection against all forms of space radiation. Advanced medical monitoring and treatment capabilities will be essential for future long-duration missions. Astronauts on missions to Mars or other distant destinations will need to be able to diagnose and treat health problems that may arise during their missions, including those related to the long-term effects of space travel. This will require sophisticated medical equipment and extensive training in space medicine. The ethical implications of sending astronauts on missions that will inevitably cause long-term health effects are profound. Space agencies must carefully weigh the scientific and exploratory benefits of space missions against the health risks to astronauts. They must also ensure that astronauts fully understand these risks and provide adequate medical care and support for astronauts dealing with the long-term consequences of their service. As we plan for longer missions to more distant destinations, the long-term health effects of space travel become an increasingly important consideration. A mission to Mars would expose astronauts to all of these health risks for a much longer period than any previous space mission. The crew would face not only the immediate dangers of the journey and planetary operations, but also the certainty of long-term health consequences that could affect them for the rest of their lives. The selection criteria for future long-duration missions may need to be revised to account for these health risks. Younger astronauts may be preferred because they have more time to recover from space-induced health effects and because the long-term consequences may be less severe for them. However, this raises questions about fairness and whether it is ethical to ask young people to accept such significant health risks. Research into the long-term effects of space travel continues to reveal new and unexpected ways that the space environment affects human health. As our understanding of these effects grows, it becomes clear that space travel represents not just an immediate risk to human life, but a long-term threat to human health and well-being. The body pays a price for every moment spent in the hostile environment of space, and that price may be collected over many years or decades. The long-term effects of space travel serve as a sobering reminder that humans are not designed for life in space. Our bodies, evolved over millions of years to function on Earth, struggle to adapt to the alien environment of space and are permanently changed by the experience. For those brave enough to venture into space, the journey represents not just a temporary departure from Earth, but a permanent alteration of their physical being. These effects represent a form of slow death, where the very act of exploring space gradually breaks down the biological systems that sustain life. While astronauts may return to Earth alive and apparently healthy, they carry with them the invisible scars of their journey, a reminder that space exploration comes at a cost that extends far beyond the duration of the mission itself. In the quest to explore the cosmos, we are learning that the price of leaving Earth may be measured not just in the risk of immediate death, but in the gradual deterioration of life itself. Death in space represents the ultimate frontier of human mortality, a final journey into an environment so alien and hostile that even the basic processes of death and decay are fundamentally altered. When a human being dies in the void of space, they enter a realm where the familiar rituals and biological processes that have marked the end of life for countless generations on Earth simply do not apply. In space, death becomes something strange and unfamiliar, a process that challenges our deepest assumptions about mortality and what it means to be human. The immediate aftermath of death in space depends greatly on the circumstances of how the person died and where their body is located. If death occurs inside a pressurized spacecraft, the body will initially behave much as it would on Earth, beginning the normal processes of decomposition and decay. However, even in this protected environment, the unique conditions of space begin to assert their influence almost immediately. In the microgravity environment of space, the normal circulation patterns that occur after death are disrupted. On Earth, gravity causes blood to pool in the lower portions of the body, creating the characteristic lividity patterns that forensic investigators use to determine how long someone has been dead and in what position. In space, these patterns do not develop in the same way, as blood and other bodily fluids distribute themselves according to the complex fluid dynamics of microgravity rather than the simple pull of gravity. The lack of convection currents in microgravity also affects how the body cools after death. On Earth, air currents help to carry away body heat, causing the temperature to drop predictably over time. In space, heat transfer occurs primarily through radiation and conduction, causing the body to cool more slowly and in different patterns than would be expected on Earth. If death occurs outside a spacecraft, in the vacuum of space itself, the process becomes far more dramatic and alien. As we have discussed in earlier chapters, exposure to vacuum causes rapid decompression, ebulism, and extreme temperature fluctuations. But what happens to a body that has already died when it is exposed to these conditions is equally fascinating and disturbing. A corpse exposed to the vacuum of space will undergo rapid decompression, just as a living person would. The gases within the body will expand, causing significant swelling and distortion. The saliva, tears, and other bodily fluids will boil away into space, leaving the body desiccated and mummified. The extreme temperature fluctuations between sunlight and shadow will cause the body to alternately heat and freeze, creating thermal stresses that can cause the body to crack and fragment over time. The preservation effects of the space environment are remarkable and unsettling. In the cold vacuum of space, with no oxygen to support bacterial decomposition and no scavengers to consume organic matter, a human body can remain preserved for potentially millions of years. The body becomes a kind of biological fossil, freeze-dried and mummified by the harsh conditions of space. This preservation is not gentle or dignified. The body swells grotesquely from decompression. The features become distorted and unrecognizable, and the skin takes on a mottled, discolored appearance. The extreme temperature cycles cause the body to become brittle and fragile, potentially breaking apart into fragments that drift separately through space. What remains is no longer recognizably human, but rather a collection of preserved biological material that bears little resemblance to the living person it once was. The psychological impact on surviving crew members of having a dead body aboard their spacecraft cannot be overstated. The confined environment of a spacecraft means that there is no way to remove the body from the living spaces, and the emotional and practical challenges of living and working alongside a corpse can be overwhelming. The constant reminder of mortality, combined with the knowledge that the same fate could await any of them, can create a level of psychological stress that threatens the success of the entire mission. In some cases, crew members have reported experiencing profound changes in their worldview and priorities after being confronted with death in space. The stark reality of human mortality in the cosmic void can strip away the illusions and distractions that normally help people cope with the knowledge of their own eventual death. In the vastness of space, surrounded by infinite emptiness, the death of a crewmate can serve as a profound reminder of the fragility and temporary nature of human existence. The practical challenges of handling a dead body in space are immense. On Earth, we have developed elaborate systems for managing death, from medical examinations to funeral preparations to burial or cremation. In space, none of these familiar processes are possible. The body cannot be buried, as there is no ground. It cannot be cremated, as fire behaves differently in microgravity and would pose a serious safety risk to the spacecraft. The options for body disposal in space are limited, and none of them are particularly dignified or comforting. The body could be jettisoned into space, where it would drift forever through the void, potentially becoming a piece of biological space debris that could pose a hazard to future spacecraft. It could be stored in a freezer compartment if one is available and large enough, but this ties up valuable resources and equipment for the remainder of the mission. Some space agencies have developed protocols for dealing with death during space missions, but these protocols are necessarily limited by the constraints of the space environment. The body might be wrapped in plastic and stored in the coolest available location to slow decomposition. In extreme cases, the body might be placed in a spacesuit and stored in an airlock or other unpressurized compartment, essentially freeze-drying it in the vacuum of space. The legal and ethical questions surrounding death in space are complex and largely unresolved. Who has jurisdiction over a body that dies in space? What laws apply when death occurs in international waters of space, such as aboard the International Space Station? How should the wishes of the deceased and their families be balanced against the practical necessities of spacecraft operations and crew safety? Different countries have different traditions and requirements for handling human remains, and these differences become problematic when international crews are involved. Some cultures require specific burial practices or prohibit certain forms of body disposal. Religious considerations may dictate how the body should be treated and what prayers or rituals should be performed. Accommodating these diverse requirements in the confined, resource-limited environment of a spacecraft presents challenges that have no easy solutions. The documentation and investigation of death in space presents its own unique challenges. On Earth, deaths are typically investigated by trained professionals who can perform autopsies, collect evidence, and determine the cause of death. In space, the surviving crew members may need to serve as investigators, photographers, and witnesses, roles for which they may be poorly prepared and emotionally unsuited. The limited medical equipment available on most spacecraft makes it difficult to determine the exact cause of death, or to preserve evidence that might be important for later investigation. The inability to perform a proper autopsy means that important medical information may be lost, potentially affecting the safety of future missions if the death was caused by a previously unknown hazard or medical condition. The communication of news about death in space to Earth presents additional challenges. The families of deceased astronauts must be notified, but the communication delays inherent in space travel can make this process awkward and emotionally difficult. A death that occurs during a mission to Mars, for example, might not be communicated to Earth for 20 minutes or more, and any response from Earth would take an equal amount of time to reach the spacecraft. The media attention that would inevitably surround a death in space could create additional pressure and stress for the surviving crew members. They would need to continue their mission while knowing that their every action is being scrutinized by people on Earth who may not understand the constraints and challenges they face. The knowledge that their handling of their crewmate's death is being judged by millions of people could add an unbearable psychological burden to an already traumatic situation. The impact of death in space on future missions could be profound. Public support for space exploration might diminish if deaths become common, or if they are handled in ways that the public finds disturbing or unacceptable. The families of astronauts might become reluctant to support their loved ones' participation in space missions if they believe that adequate provisions have not been made for handling death with dignity and respect. The development of better protocols and equipment for handling death in space is an ongoing area of research and planning. Some concepts include specialized body storage systems that could preserve remains while minimizing the impact on crew psychology and spacecraft operations. Others involve the development of space-based cremation systems that could reduce remains to ashes that could be more easily handled and disposed of. More advanced concepts include the possibility of returning bodies to Earth for traditional burial, though this would be extremely expensive and might not be possible for missions to distant destinations. The development of space-based burial sites, perhaps on the Moon or on asteroids, has also been proposed, though such facilities would require enormous investments of resources and technology. The philosophical and spiritual aspects of death in space force us to confront fundamental questions about human nature and our place in the universe. The traditional human experience of death has always been tied to the earth, with burial in the ground or scattering of ashes connecting the deceased to the planet that gave them life. Death in space severs this connection, creating a form of mortality that is truly alien to human experience. For many people, the idea of dying in space and having their body drift forever through the cosmic void is deeply disturbing. It represents a form of eternal exile from the earth and from the human community. The body becomes a permanent wanderer in the emptiness between worlds, never finding rest or reunion with the planet that created it. Others find a certain poetry and grandeur in the idea of death in space. They see it as the ultimate form of exploration, a final journey into the infinite mystery of the cosmos. From this perspective, death in space represents a merging with the universe itself, a return to the cosmic dust from which all life ultimately comes. The religious and spiritual implications of death in space vary widely among different faith traditions. Some see space as just another part of God's creation, no different in spiritual terms from any location on Earth. Others believe that the soul or spirit is not bound by physical location and can find its way to whatever afterlife awaits, regardless of where the body dies. Still others worry that death in space somehow interferes with the soul's journey or prevents proper religious observances. The future of human space exploration will inevitably involve more deaths in space as missions become longer, more complex, and more numerous. A permanent colony on Mars would almost certainly experience deaths from various causes, from accidents to medical emergencies to simply old age. These communities would need to develop their own traditions and practices for handling death in an environment that is fundamentally different from Earth. The development of space-based medical facilities capable of performing autopsies and preserving bodies for eventual return to Earth might become necessary as space communities grow and mature. The establishment of space cemeteries or memorial sites could provide a sense of permanence and continuity for space-dwelling humans, while honoring those who have died in the pursuit of exploration. The study of death in space also provides insights into the nature of life itself. By understanding how death unfolds in different environments, we gain a deeper appreciation for the conditions that make life possible and the delicate balance of factors that sustain it. The harsh realities of death in space serve as a reminder of how dependent we are on the specific conditions of Earth for not just life, but for death with dignity. As we stand on the threshold of becoming a multiplanetary species, we must grapple with the reality that death will follow us wherever we go. The void of space will claim some of those brave enough to venture into it, and their deaths will mark the ultimate sacrifice in humanity's quest to explore the cosmos. These deaths will not be in vain if they help us learn how to live and die with dignity in the hostile environment of space. The final frontier is not just about exploring new worlds and discovering new forms of life. It is also about confronting the ultimate mystery of death in a setting that strips away all the familiar comforts and rituals that have traditionally helped humans cope with mortality. In the vast emptiness of space, death becomes both more terrifying and more profound, a reminder that even as we reach for the stars, we remain fundamentally human, mortal beings seeking meaning and dignity in the face of the infinite void. As we reach the end of our journey through the most horrific ways to die in space, we are left with a profound understanding of just how fragile human life truly is when we venture beyond the protective embrace of our home planet. Space, for all its beauty and wonder, remains fundamentally hostile to human existence. Every breath taken in space, every step on an alien world, every moment spent in the cosmic void represents a triumph over forces that would otherwise claim human life in an instant. The dangers we have explored throughout this exploration are not merely theoretical concepts or distant possibilities. They are real threats that have already claimed lives and will continue to do so as humanity pushes further into the cosmos. The vacuum of space has no mercy for the unprepared. Extreme temperatures show no favoritism to the brave. Radiation cares nothing for human ambition. These forces of nature operate according to physical laws that preceded humanity by billions of years and will continue long after we are gone. Yet despite these overwhelming dangers, humans continue to venture into space. We do so not because the risks are small, but because the potential rewards are so great that they justify accepting those risks. Every space mission represents a calculated gamble, a bet that human ingenuity, courage, and determination can overcome the hostile environment of the cosmos long enough to expand our understanding of the universe and our place within it. The astronauts and cosmonauts who have given their lives in the pursuit of space exploration did not die in vain. Their sacrifices have taught us valuable lessons about the dangers of space travel and have led to improvements in spacecraft design, safety procedures, and mission planning. Each tragedy has made future missions safer, even as it has reminded us of the ultimate price that space exploration can demand. The courage required to venture into space knowing these dangers is almost incomprehensible to those of us who remain safely on Earth. Astronauts must not only master incredibly complex technical skills and maintain peak physical condition, but they must also possess the psychological strength to function effectively, while knowing that death is always just one system failure away. They must be able to look into the infinite void of space and not be paralyzed by the knowledge of their own mortality. This courage is not reckless abandon or disregard for safety. It is a calculated acceptance of risk in service of a greater purpose. Astronauts understand the dangers they face, and they work tirelessly to minimize those risks through training, preparation, and careful attention to safety procedures. But they also understand that some level of risk is unavoidable when pushing the boundaries of human experience and knowledge. The families of astronauts share in this courage, though their sacrifice is different and in many ways more difficult. They must watch their loved ones depart for missions that could end in tragedy, knowing that they may never see them again. They must live with the constant awareness that a phone call could bring news that will change their lives forever. Yet they support these missions because they understand the importance of space exploration for the future of humanity. The engineers, scientists, and mission controllers who support space missions also share in the responsibility and the risk. They know that their decisions and their work directly affect the safety of the astronauts who depend on them. A single mistake in design, calculation, or procedure could lead to catastrophic failure and loss of life. This knowledge creates a level of responsibility and pressure that few professions can match. The broader human community also bears responsibility for the risks taken by space explorers. When we celebrate the achievements of space missions and marvel at the images and discoveries they provide, we are also accepting the moral weight of the risks that made those achievements possible. We are saying that the knowledge and inspiration gained from space exploration justify asking some members of our species to risk their lives in the cosmic void. This moral calculus becomes more complex as space missions become longer and more ambitious. A journey to Mars will expose astronauts to radiation levels and isolation periods that far exceed anything previously experienced by human beings. The health effects of such a mission are largely unknown, and the psychological challenges may prove insurmountable for some crew members. Yet, we continue to plan for such missions because we believe the potential benefits justify the risks. The technology that protects astronauts from the dangers of space continues to improve, but it will never eliminate all risks. The laws of physics that make space so hostile to human life cannot be repealed through engineering or ingenuity. We can build better spacesuits, more reliable life support systems, and more robust spacecraft. But we cannot change the fundamental fact that space is an environment where humans were never meant to live. The psychological impact of understanding these dangers extends beyond the astronauts themselves to everyone involved in space exploration. Knowing the horrific ways that space can kill creates a sobering awareness of human vulnerability that can affect how we view our own lives and mortality. The vastness and hostility of space serve as a powerful reminder of how precious and fragile life really is. This awareness can be both frightening and inspiring. The knowledge that we are vulnerable beings living on a small planet in an infinite cosmos can make us feel insignificant and alone. But it can also inspire us to value life more deeply, to appreciate the remarkable conditions that make life on Earth possible, and to work together to protect and preserve the only known oasis of life in the universe. The exploration of space also forces us to confront fundamental questions about human nature and destiny. Are we meant to remain forever bound to the Earth that gave us birth? Or are we destined to become a spacefaring species that spreads life throughout the cosmos? The answer to this question will determine how we approach the risks and sacrifices required for space exploration. If we choose to remain earthbound, we can minimize the risks to human life by avoiding the dangers of space travel. We can focus our energies and resources on solving the problems of our home planet and creating a sustainable civilization that can endure for millennia. This path offers safety and certainty, but it also means accepting permanent limitations on human growth and exploration. If we choose to become a spacefaring species, we must accept that some lives will be lost in the process. We must be willing to send our best and brightest into harm's way, knowing that some of them will not return. We must develop technologies and procedures that minimize risks, while accepting that those risks can never be eliminated entirely. This path offers unlimited potential for growth and discovery, but it comes at a cost measured in human lives. The history of human exploration suggests that we will ultimately choose the path of expansion and exploration, despite the risks involved. Humans have always been driven to explore new frontiers, to push beyond the boundaries of the known world, and to seek out new challenges and opportunities. The ocean depths, the polar regions, and the highest mountains all presented deadly dangers to early explorers. Yet humans persisted in exploring them until they became familiar and manageable. Space represents the ultimate frontier, the final challenge to human exploration and expansion. The dangers are greater than anything we have faced before, but so are the potential rewards. The knowledge gained from space exploration has already revolutionized our understanding of the universe and our place within it. The technologies developed for space travel have improved life on Earth in countless ways. The inspiration provided by space exploration has motivated generations of scientists, engineers, and explorers. As we look toward the future of space exploration, we can expect that the dangers will evolve and change, but they will never disappear entirely. New technologies will create new risks while solving old problems. Longer missions will expose astronauts to dangers that we have not yet fully understood. The establishment of permanent space colonies will create entirely new categories of risk and challenge. The brave men and women who choose to venture into space in the coming decades will face dangers that we can barely imagine today. They will push the boundaries of human endurance and capability in ways that will test the limits of both technology and human nature. Some of them will not survive the attempt, adding their names to the roll of those who have given their lives in the pursuit of space exploration. But their sacrifices will not be meaningless. Each mission, whether successful or tragic, adds to our understanding of how to live and work in space. Each lesson learned makes future missions safer and more successful. Each tragedy motivates us to work harder to protect the lives of future explorers while continuing to push the boundaries of human achievement. The fragility of life in space serves as a reminder that every moment of human existence is precious and should not be taken for granted. The astronauts who risk their lives in space do so not just for themselves, but for all of humanity. They carry with them our hopes and dreams, our curiosity and ambition, our determination to understand the universe and our place within it. When we look up at the night sky and see the stars twinkling in the darkness, we should remember that some of our fellow human beings are out there among those stars, risking everything to expand the boundaries of human knowledge and experience. They face dangers that would terrify most of us, yet they do so with courage and determination that inspires us all. In the vast expanse of the cosmos, human life is indeed fragile and temporary, but it is also precious and meaningful. The fact that conscious, intelligent beings like ourselves have emerged from the cosmic dust and learned to contemplate the universe is perhaps the most remarkable achievement in the history of the cosmos. The continuation of that achievement, the expansion of human consciousness and capability into the depths of space, justifies the risks and sacrifices required to make it possible. As we rest beneath the stars, contemplating the infinite mysteries that surround us, we can take comfort in knowing that brave explorers are working to unlock those mysteries, even at the cost of their own lives. Their courage and sacrifice represent the best of human nature, the determination to seek knowledge and understanding regardless of the personal cost. In honoring their memory and supporting their missions, we participate in humanity's greatest adventure, the exploration of the final frontier that surrounds our small blue planet in the cosmic dark.